The topic for today is going to be waves. Now, there are all kinds of waves that surround us everywhere in every single aspect of our life. We might have it in the form of electromagnetic waves that were discussed in the video yesterday. It could be the sound that you're hearing right now. It could be somebody that's tapping their foot on the floor. It could be a person that's strumming a guitar. It could be a kid that's on a swing, moving back and forth, back and forth. It could be two people on a teeter-totter. There's all kinds of examples that we can use for waves. What we're going to do is we're going to look at what are some examples of these oscillating waves, and we're going to look at what the properties of those waves are. Okay? So the goal for today, identify some simple examples of oscillators. You're going to want to be able to determine the frequency and the period of these oscillators, and then by the end of the class period, be able to graph some of these simple harmonic motions of these objects that are moving back and forth, oscillating. We won't get to the natural frequency today, but we will get to that at another date. All right, so what exactly is harmonic motion? That's what we need to start with. So if we're trying to describe what harmonic motion is, here we have just an example of a pendulum. Okay, so our pendulum, we have a string that's tied, and you have this weight that's at the bottom. Now, this weight that's sitting down at the bottom, before it is disturbed, it is in its equilibrium state. It's not moving around. It's just at rest. It's at equilibrium. Now, once we apply a little bit of a force to this, what we're going to do is we're going to add some energy, and that object, that weight that's suspended at the end, it's going to start to move back and forth, back and forth. Okay, now that is what we would describe as an oscillating object, something that's moving back and forth. Okay, so everything that we have done in class so far has all been in a linear fashion. You know, a car takes off and it's going to go 20 meters per second. It's heading north. We might have a rocket that's blasting off into the sky at an acceleration of 3 meters per second squared. Everything so far has been in a linear fashion, something that is in a straight line like this. Okay, but when we're talking about oscillators, the example I just showed you with the pendulum swinging back and forth, that's what we would describe as an oscillating object that is in a harmonic motion, something that's going to continue to repeat itself over and over and over again and again. Okay, so the kid on the swing right here, we have the kid that's on the swing. As soon as she has some energy that's put into the system being her on the swing, she will take and move back and forth. All right, we're going to try to figure out what the period and the frequency of that type of motion actually is going to be. All right, so our pendulum, just something that's going to be moving back and forth. That's what we're going to use through this whole idea of trying to figure out what our properties are. So if our pendulum, our bob on our pendulum here, the weight that is suspended right here, okay, if it is held at that position, okay, and released, gravity is going to cause that pendulum to start to swing downwards. All right, now, once it gets to the bottom, it's going to continue moving until eventually it doesn't have any more energy to get that bob or that weight moving upwards into the air anymore, and then it's going to start to fall back down. So if it continues without any loss of energy, it's just going to continue swinging back and forth. Now, if we have one cycle, now we're going to start right here on this side. If we start right here and that pendulum swings down and gets to the highest point on the opposite side and then swings back to the originating spot, we say that that has completed one cycle. All right, one cycle is one back and forth motion. All right, so it's very important that you understand what a cycle is. It's just one single movement back and forth. If we were talking about two people on a teeter-totter, if we have, let's say that this person starts upwards in the air, well, in this particular example, this kid would go down and then back up again for one complete cycle to take place, okay? One back and forth motion. So that back and forth motion, as it's taking place, as the pendulum starts to move forwards and then swings backwards, it's constantly speeding up and slowing down. All right, so the pendulum sitting right here, okay, or the kid on the swing, it doesn't matter whichever way that you're going to look at it. It's swinging and it stops, and then it picks up speed, and then it starts to slow down until it stops, and then it's going to continue to pick up speed, slow down, stop. So the speed is constantly changing from the very moment that that pendulum or that kid on the swing is released, or the person on a teeter-totter starts to move up and down. And what we're going to do now is we're going to look at how much time does it take for one of those cycles to take place, or how many cycles can take place in 1 second. So we're going to try to figure out what the frequency is of those. All right, so we just had two terms. We had period and we had frequency. So the first term that we need to look at to have a basic understanding of is this guy right here. What exactly is the period? The period is the time for one complete cycle to take place. So if we have the kid that's sitting on the swing here, okay, if they start right here, okay, how much time, if we started our stopwatch, how much time does it take the kid to swing all the way over and then come all the way back? What is the time, if we had that being recorded, how much time does it take for one swing, and again, back and forth, to take place? All right, that's what the period actually stands for. We go on, the other term that we're trying to figure out or to try to identify is frequency. Frequency is a little different than the period, but they are related to one another. Frequency is the number of vibrations or the number of cycles per second. So the key here is per second. So frequency, our kid on the swing set right here, the average swinging back and forth, it might take 1 to 2 seconds for that kid to actually move from this position here, swing all the way over, and then back. All right. Now that's a pretty slow oscillation. When you're looking at a guitar string and you strike the actual strings on the guitar, they're going to be vibrating a whole lot faster than what that kid on the swing is going to be moving back and forth. All right. So we wouldn't want to just say how many vibrations there are. We want to take and identify how many vibrations are occurring per second. And that tells us how many vibrations per second. It tells us what the frequency of that string right here would be going at. All right. Now, later this week, what we'll do is we'll have a sound test where we're going to see how good your hearing is. And usually as you start to get older and older and older, your hearing starts to go bad on you. All right, you start to lose the higher frequencies. So you guys, when we start the hearing test, you're going to be very annoyed when we get to the very end of it, when I can't hear past that 15,000 hertz, the 15,000 vibrations per second. You guys, you'll be able to hear that easy. Me, not so much. Okay, so the period and frequency, I said that they're different, but they are related. Now, they're inversely related, all right? And we're going to look at a formula that's going to help to explain that. Now, something that I did jump into, I said that the unit for this, I said that Our guitar string would be 220 hertz. Hertz is just the unit of measurement that we use. Now, another way that you could look at hertz is the number of vibrations per 1 second, like that. This little thing right here, that probably, if you write that down, that's going to pay off when you get to the homework for tonight. Okay? So, if you have a little bit of troubles understanding what I'm talking about, you can go to YouTube, check out this guy. He's a little more energetic than I am, but the same material is going to be discussed. Okay, we need a formula. We're talking about how these two things are related together. What we need is, on your formula sheet, these two things written down. All right. If you struggle a little bit with your rearranging of equations, you could always do a circle diagram, something like this. And we could put up top, you could put 1, you could put T, and then we could do our fancy F right here for the frequency. Now you don't want to make this guy right here, you don't want to make that a capital F, because we've already used the capital F for force. Don't do that, okay? Use your little cursive S right there, or cursive F right there. So what do these two letters, what do these two variables stand for? Well, the first one here, the T, obviously we've used T for time in the past, okay? So it only makes sense that the T stands for seconds or time. Now remember that the time that we're looking at is described as the period. And the period is going to be the time for one cycle to occur. One back and forth motion on the swing set. Okay. The next one that we're going to take a look at here, we have our frequency. The frequency, that is the number of vibrations per 1 second. All right. And we're going to look at an example in when we're going to the other side. If we're trying to find the frequency, you rearrange your equation. You've got F equals 1 over T, or if you're trying to find the time, you put, or the period, you put 1 over F. Pretty easy formula to work out. All right, so let's do an example of this. On this page, you have the period of an oscillator is 2 minutes. What's the frequency of this oscillator in hertz? So we got to figure out how many vibrations per second is this pendulum actually going to be moving back and forth, right? So we know that this thing right here, it says the period of the oscillator is 2 minutes. So T equals 2 minutes, but we don't want it in minutes. We always want this time frame to be in seconds. So you're going to have 120 seconds right here. All right, what we're trying to figure out is what is, and I just did a no-no there. All right, we want this to be our italicized F right here. So what is the frequency of this? And again, frequency, vibrations per 1 second is what we're going to look at. All right, from our formula that you had. Okay, now for the people that need the little circle diagram, here we go. I'm trying to find the frequency of this thing. So if that's what I'm trying to find, I'm going to cover it up. That means I'm going to take 1 divided by the period, 120 seconds. And that should come out, if we put that into the calculator, we have 1 divided by 120. You come up with 0.008. Now there's 2 ways that we could write down our unit of measurement for this. You could put, now that is rounded off, by the way. You could put down 0.008 vibrations per 1 second, or you could simplify that and just say 0.008 hertz is what you could have. All right, now we're going to take a look at this paper right here. I want all of your answers put onto that second piece of paper that I have onto this, but we're just going to look at an example. We're going to do number 9 together here. Number 9, it says, by the way, if you get stuck on something, all you got to do is come up here and all the formulas are right there for you. Okay, we have number 9. It says an oscillator makes 360 vibrations in 3 minutes. Now, this right here, that's the number of vibrations in 3 minutes. Okay, so we have 360 vibrations in 3 minutes like this. It says, letter A, how many vibrations does it take? How many vibrations does it make in 1 minute? Well, if you know how many vibrations it has in 3 minutes, all we have to do is divide that out by your 3. And what we come up with for part A here, is you come up with 120 vibrations per 1 minute. Okay? Question B. Question B here, how many vibrations does it make in 1 second? Well, if we have 120 vibrations in 1 minute, if we just change our unit of measurement now to seconds, 1 minute is 60 seconds. So you take your 120, you divide it by 60, and you come up with 2 vibrations per second is what that's going to be. All right. It says, what's the period for this? All right. Now, period for part C here, if you're trying to find the period, you'd use that formula 1 over F. All right. F is the frequency, but how do you know what the frequency is just yet? Well, it's kind of hidden away in plain sight here. See, part D, if we look at part D first, it says, what is the frequency in hertz? Frequency is the number of vibrations per second. And if you look right here, you already know the number of vibrations per second. So if the number of vibrations per second is 2, that means that the frequency right here is 2 hertz. Yes, those two things, they are the same. The number of vibrations per second and the frequency, they're the exact same thing. So we can plug that frequency in. We have 1 divided by 2 hertz. So that means the period, the time necessary to complete 1 back and forth motion is 0.5 seconds. All right, so the time required, this thing might be vibrating 360 vibrations in 3 minutes, but for every single one of those 360 vibrations, it takes 0.5 seconds to complete 1 vibration back and forth. All right, so what you need to do is answer up the rest of these questions here for tonight. They're not difficult, they're pretty straightforward, and you have to do that on the separate piece of paper. All right, what we're going to look at next is if we have something that's vibrating back and forth, the amount of energy that you put into swinging the kid on a swing. All right, so if you have this kid and they're sitting on the swing like this, all right, now if this kid is sitting on a swing and maybe if I can get it, I don't think it's going to work for me. It was working just fine a minute ago. All right, so this kid, hopefully, there we go. All right, so this kid, if they're sitting on a swing and no one's pushing them, all right, they have no friends to give them a shove. They don't know how to swing on a swing. They're at rest. They're in an equilibrium. They're not moving back and forth at all. There's no harmonic motion here. Well, some passerby sees them, feels sorry for them, and gives them a little bit of a shove. Now, if it's just a little shove, you'll see that the kid doesn't move very far back and forth. Their amplitude is very small. There's not a lot of energy that was put into them swinging. All right, now, here you go. You walk by and you see some poor kid sitting on a swing and you're a mean person. I don't know, maybe you want to make sure the kid has a good time. So what do? You give him a gigantic shove. Okay, so right here, if they go from equilibrium and then all of a sudden they get swung all the way up here, the only way that they're going to get up that high is if you put a lot of energy into that system, into the kid moving back and forth. So the greater the distance, the greater the angle off of our equilibrium, our rest position, represents the amount of energy that's put into the system, and that's what we refer to as our amplitude. Our amplitude is going to tell us how far off of our equilibrium or rest position do we get, and that's related to the amount of energy that you put into a system. Okay? If you have some troubles understanding this, there is another video that you can check out that helps to identify our amplitudes of our waves. Okay? So amplitude, how high do we actually measure the person swinging on a swing back and forth? How intense is an earthquake? How high are waves? Well, what we do is you could measure from the trough, okay, the lowest point right here, to the crest, what that distance is, and then you could take and divide that by 2, or as the person on the swing example, if we get that rest position right in between, if we measure from that rest position or equilibrium to the highest point, or if we look at it from the rest position to the lowest point, that's another way that we could measure that. Okay. So, how do we get our amplitude? You take the high point and the low point, you get the total distance there, you divide that by 2, and that's going to tell you your amplitude. Now, the greater the displacement, the greater the amount of energy that's going to be associated with that particular wave. All right. On this, we're going to measure the amount of amplitude in terms of degrees or centimeters. All right, so degrees, that's pretty easy to understand. You just look at what theta is right here. Now, our centimeters, you could kind of think of this as, you have a seismograph, and here is the needle of the seismograph right here. And as the earth starts to shake back and forth, how much movement that is occurring by the base of that seismograph is going to indicate the distance measured on our piece of paper from the pen marking on it. All right. So in this paper right here, if we again look at our example of the seismograph, all right. So I'm going to grab this guy, move it down. Okay. On that seismograph, the pen right here, the red pen, that's going to be our marker. Okay. And then the box down below here, this thing, the green box, that's going to be the big roll of paper that's going to mark the amount of displacement the Earth is experiencing as an earthquake is taking place. So as this base is moving back and forth, what it is going to create is a motion on your paper that looks something like this. All right, now that's an example of a wave, a harmonic wave. If you don't like the example of the seismograph, fine. Don't use the example of the seismograph. Maybe if you have a kid that's on a swing and they're dragging their feet on the ground and somebody's pulling a piece of paper or something out from underneath their feet, what kind of motion is occurring? The back and forth motion. Okay. Well, what information can we get from this then? We have, for the first one, it says, what is the amplitude for the vibration for the first one? Amplitude, how high off of equilibrium do we have this? Equilibrium, a rest position right here. How high up or how low will our wave be displaced? In the first example, I go up to my crest and I come over to the left-hand side and I see that this thing says it's a 5-degree angle. All right, now you're going to have to solve the one for letter B here on your own. On the back side, last thing that we're going to do today is I'm going to show you the basic setup for this, and it's not much different than what you see right here. So we have our angle, our degrees, and the position is on the y-axis, and you see the time is always on the x-axis. So our first example, it says it's in centimeters, so I'm going to go 0, 1, 2, and these are our distance, our position in centimeters right here. So we have the position, centimeters, we go -1, -2, and then for my time, I'm just going to go with 1 second, 2 seconds, 3, and 4. You can put as many over as you want. So our magnitude of this is going to be 2 centimeters. I know that I'm going to have an arch that is going to max out up here somewhere, and the trough is going to max out down here like this. But I need to have one complete cycle within 1 second. So this thing has to go up and then back down again in 1 complete second, 1 cycle, 1 back and forth motion in that time frame. So what we can say is if I start it here, and there's all kinds of different places that we can start it at, but I'm just going to start mine at the equilibrium here. I know that by the time that I get to my 1 second, I've got to be back to the start position here. So I need to go up, down, and back again within 1 second. So maybe I should have spread that out a little bit more. You might want to make yours a little bit wider. So maybe we say, I don't know, we'll go with this one right here. We'll go, that would be 1, and that would be 2 here. That might make it a little bit easier for you to complete this. But if you go up, down, and back again, that's just going to be 1 cycle. All right, you organize yours however you want them to look, whatever your spacing is going to be, okay? But what you've got is the rest of these two, A and B, that you have to complete for tonight. So those 2 pages, this one right here, all of those periods and frequencies, and then the amplitudes on this. All right, those are due tomorrow.